All right, let's start. So can everybody see the slides?
Yep.
Okay, great. So first, this is our last lecture of this semester. So I have made an announcement about the final exam. It will be April 24th from 10:30 to 12:30, 10:30 a.m. to 12:30 p.m. So the schedule, detailed schedule is in the course webpage as well. So if you feel doubt about that, you can check out our course webpage. It has already been highlighted in the bolded font. And so today we're gonna first spend like 20 minutes also to give a brief review for the final exam. And then we're gonna give some practical suggestions for machine learning applications. Okay, so the exam will be held online, right? We know that it will be conducted on campus. And some student asked me yesterday about like what kind of problems you guys might need to solve and how many problems, etc. So basically, the most commonly used problems in online exam, like single choice, multiple choice, like text descriptions, and etc. But you will not be asked to derive something with mathematical steps. If you really want to do that, it's really good. And or if you want to express some equations, you can write it in kinds of text format like LaTeX, syntax. I assume everybody now is very familiar with LaTeX. Feel free to do so, but it's not required to do that. And the exam, if you are given some kind of text description problems, the key is to point out the point. I mean, point out the key questions. Like probably I'll ask you what is overfitting, or why overfitting is bad. How can I avoid overfitting? Those kind of steps. I'm pretty much sure that won't ask you to derive a lot of like mathematical stuff, but you need to hit the point. Okay. And the time, I mean, the duration of this exam, just a standard duration, just 2 hours. But I would like to tell you guys, like, do not be like nervous on that, because usually online exam will be a lot easier than paper exam in a classroom because of the special situation and circumstances. We cannot conduct any in classroom exams. That means our final exam will be relatively much easier than before. So that's a good news. Right? So yeah, this is a notice again, right? So hopefully you won't miss that because time is here, it's fixed, right? And also, if you want to confirm the schedule, you can click this link and look at the course webpage. Okay, so here is the policy for the final exam. So first is open book and open website. So at the beginning of this semester, we mentioned that at that time we assumed that our final exam will be conducted in classroom. So at that time, I told everybody cell phones and laptops, all those kind of things are not allowed. But right now we have to do the online exam. So we still have the policy to open book. If you want to look at something from a website, that's fine. But do not search questions online. Do not post questions online. If you can't help doing that, I'm pretty much sure you won't find anything useful. I won't copy any questions from online. I'll double check. I want to make sure that my problems won't have any overlapping with the questions and problems online. Okay. And single and multiple choices and test descriptions. Descriptions do not need to write math, but you're welcome to write any kind of math in LaTeX grammar if you want, but it's not obligatory. And one thing that could be important, that problems can vary for different students. So basically, the mechanism is as follows. We're gonna create a group of questions for different problems, and the system might randomly pick up one problem for you, but don't feel like because the difficulty level of those problems are almost the same. Like the only issues are they might be asked in different ways, and they have different settings on that. That means you cannot call your friends and say, okay, let's say whether you got A and I got A, or you got B and I got C. That won't work. That definitely won't work. Okay. So any questions so far regarding the schedule and regarding the policy? So everybody is comfortable, right? Okay, great. So the coverage. So because we don't have any midterm exam, so the coverage is the content which probably appears in a final exam will cover the whole semester. So here are suggestions. If you really want to do a very effective and efficient review, I'll suggest you guys to review the lecture slides. You do not need to look at any textbook. If you have enough time and energy, you can do that, but it might not be very efficient to exam preparation. And also carefully go through the paper problems in homework assignments, although the form of our final exams won't be like paper problems like you write down everything. It won't be like that because of physical constraints, but the idea, the knowledge point we might examine you are fully reflected in the homework assignments. So reviewing homework problems will be very beneficial. Okay. So now let us just give you a general overview of the semester. We won't cover every detail. I just want to give you a lead to pass through all the things we have discussed. Right? So throughout this semester, we have talked about first where we introduced the definition of machine learning, right? And then based on this framework, we introduced a variety of learning models and algorithms, and we'll talk about the principles to design those learning models and algorithms, like PAC learning framework, right? Computational learning theory, like regularized risk minimization principle, regularized risk minimization principle, Bayesian learning, etc. Right? Under different learning principles, we develop different types of learning models and algorithms. And also we introduce a little bit theory. It's very superficial coverage of the theory, but just give you the guidance on that, right? Ideas about learning theory, and also we spend a lot of time in implementation and practice, right? We're not doing everything on paper. You have to turn your algorithms into the code, right? And test. So what is the concept of learning, right? So we introduced several introductions, but I think the best or the most rigorous definition came from Tom Michel in 1999, right? He said a computer program is said to learn from experience E, which is often referred to as training data, right? With respect to some tasks of task T. So T can be regression, can be classification, and performance measure P, right? Like accuracy, right? Like a square error, etc. Right? If the performance of this program at tasks in T measured by P improves with experience E, basically means that okay, if your program can improve the performance in some particular task after training, then you can say okay, your program can learn something from the training data. And based on this general definition, we give the formulation of machine learning, right? So to construct a machine learning algorithm, especially supervised learning algorithm, right, we need to specify several concepts. First, what is the instance space? So second, what is the label space? So the instance space are a set of examples that need to be classified. So for example, if your task is to predict the type of the news, right, like politics, like entertainment, like health, and all kind of stuff, right? So the instance space will consist of all possible news, right? And the label space is determined by the task, right? If your task is to is regression, meaning that you're going to predict some real values, then your label space consists of real values, right? If we're doing prediction, like we're predicting whether the stock price will arise or go down tomorrow, then you're doing binary classification. Your label space consists of only two labels, right? And if you do multi-class classification, then your label space consists of a set of discrete labels, right? So label space is determined by the task, the machine learning task you want, right? And then our fundamental assumption is that there is some kind of ground truth or target function which maps the instance space to the label space. And we know there exists such a ground truth, but we do not know that. So the goal of machine learning is to find this target function or find some approximation to this target function. In other words, we can view learning as a search over functions, right? So this is our general formulation of machine learning. And but how do we conduct the search? Right? That's where the training data should kick in, right? So training data actually help us to or guide us to search this target function or the close approximation to this target function. We need to design some learning algorithm, right? And we feed the learning algorithm with pairs of the training input and ground truth labels, right? X1, fx1, x2, fx2, to xn, f of xn, right? We call it label the training data. And then we feed this training data to learning algorithm. Then the learning algorithm is going to search over the hypothesis space, which consists of all possible candidate functions, right? And we just pick up the hypothesis who performs well, who fits well the training data, right? We will that function as a good candidate or good approximation to the target function. Right? So finally, we produce this learn function g from x to y, right? So we view this hypothesis as good approximation or even the ground truth function. Right? This is how learning algorithm works, right? So this is a supervised learning protocol, and of course we can think of other protocols, right? For example, we can remove the labels. Right? Suppose the training data do not have labels, do not have f of x1 to f of xn, only have unlabeled inputs x1 to xn, then this supervised learning becomes unsupervised learning. Of course, we don't have time to introduce unsupervised learning, but perhaps everybody knows k-means, right? But this classical clustering algorithm, this is a typical supervised learning algorithm because you don't have any labels on the training set, right? And semi-supervised learning, like partial training data are labeled, partial training data do not have label. So we call it semi-supervised learning. So in the supervised learning framework, we have introduced a variety of learning models. Maybe you still have an impression that our very first learning algorithm our learning model is called decision trees, right? Decision trees is a way to summarize data into a tree structure, and we can extract prediction rules from the path starting from the rule node to the leaf nodes, right? One path forms a prediction rule, right? The decision trees can be seen as a conjunction of such prediction a prediction, conjunction of such kind of prediction rules, right? Although it's pretty simple, but it's very widely used and it's very useful. It's very widely used. Right? So then, based on decision trees, we talk about how can we further improve it, right? We introduced the ensemble learning framework, boosting and ensembles, right? So the classical boosting algorithm called ADA boost. So what's the idea of ADA boost? Anyone give me a hint?
Using multiple stumped decision tree to improve the performance.
Yeah, exactly, right? So the idea is that, okay, I'm gonna first train a simple decision tree to fit data. Then based on, I want to amplify the errors I have made, right? And by downweight the correct prediction I have made, then I have a reweighted training samples, and I feed them into another decision tree model to train another model, right? And then I continue to pick up my mistakes and amplify it into reweight the training examples and train the third decision trees. In this sequential reweight and retrain procedure, we can collect a set of decision trees, right? Then our final prediction is a combination of those set of decision trees. It's called boosting, right? So another ensemble learning approach is called random forest. Random forest doesn't need to be like do sequential, right? Because the training of each decision tree is not dependent on the previous step, right? We do not reweight training examples. We just run this sample subset, or even do the bootstrap sample of the training data. And for each bootstrap sample, we train a very complicated, very wide and very deep decision trees, and we just average the prediction of those decision trees. So what's the key benefit of random forest? Why random forest can improve? Still have an impression? We actually do some quantitative analysis, right? Yeah, we do some analysis. We decompose the generalization error into a summation of the bias and variance, right? So overfitting usually means that you have a very small bias because you're training, because on average you're training, you fit the training data so well that on expectation your prediction is not too far away from the ground truth. But the problem is that when you vary the number of training examples, vary the training set, because you fit training data so well, prediction can be very, very different. So it causes a problem of large variance, right? So, but if you do the random forest, you train like 100 very deep trees with 20 levels, 30 levels, right? Each tree has small bias but very large variance. Now you average their prediction, you actually effectively reduce the variance. Right? So the key benefit of random forest is it can reduce variance, and then it can reduce the overall generalization error. Right? So this is very important. I might not ask you to write down some pseudo code to implement your ADA boost or random forest, but you need to tell me how random forest generally works and why it works. And then we talk about least mean square method for linear regression, right? We talk about very commonly used, although looks pretty simple, right? So we talk about linear regression, we talk about perceptron, right? Perceptron is a mistake-driven training algorithm, right? We process training examples sequentially, one by one, right? If there's no update, if there's no mistake in predicting the current example, just stay idle, right? I only update my model when there's when there is a mistake, right? So you need to be clear about the updating rule of the perceptron, right? And why it makes sense, right? And after that, we introduced a very successful and very dominant classifiers in machine learning areas called support machines, right? So why it's called support machines, right? Where does the support vector come from, right? So we need to be very clear about how the objective or learning objectives of vector machines are derived. Right? So we need first to know, okay, what is the basic idea of the computational learning theory, right? What is agnostic learning? What is the generalization error bound, right? So when we tighten the generalization upper bound, generalization errors upper bound, we're actually trying to maximize the margin of the linear classifier, right? And then we turn the maximizing, we turn the margin maximization principle into a optimization problem, right? So we use some assumption, right? We use some observation that if you do the linear classification, you can scale your weight and bias parameter to arbitrary level. It doesn't change, right? So we can largely simplify the optimization problem itself. Then we'll get our primal definition of SVM, right? So you need to be very clear about this logic chain, like how from the original theoretical result, agnostic learning results, to the final objective, right? And then we talk about hard SVM, we talk about soft SVM, right? How can we, why should we use soft SVM? Why shouldn't we just train hard SVM, right? And how can we deal with soft SVM, right? And we introduce slack variables, and how can we turn this primal domain, a primal problem into the dual problem, right? What is KKT condition? How can we further simplify the dual problem of SVM? And from the definition and from derivation of the solution for the dual, we derive the concept of the support vectors. So all those kind of stuff, as SVM is very big and important topic in our class. So be sure that you get everything. You need to understand the details. You're not required to like memorize or recite the form of those SVM objectives, right? But when I ask how do you derive this from this, derive this from this, you should have no problem. Okay. And also we talk about like how do we generalize linear model to nonlinear models, which is called kernel trick, right? So the kernel trick essentially is an efficient trick to compute the inner product between two vectors after high dimensional feature mapping. Like kernel function can do everything in an original feature mapping, right? So we just plug in the kernels into the inner product so that we can extend our linear model to nonlinear models. And we'll talk about kernel perception. This is your homework, right? And kernel SVM. And then the other very important topic in the remaining in the last second half of our semester is artificial neural nets, right? So the definition of artificial neural nets is pretty straightforward, right? Layer by layer, but you need to be very clear about backpropagation procedure. Right? So of course, I'm gonna ask you to calculate some backpropagation results, but not require you to write down every details. But you need to be able to illustrate how you calculate them. Okay, and then we'll talk about logistic regression and naive Bayes. So although you're not required to implement naive Bayes in homework, right, because of the schedule, right? It's the very last topic we mentioned, but very probably we're gonna talk about naive Bayes in the final exam. Okay. So also we generally we can view the machine learning models according to the complexity model, right? So like linear models and non-linear models. Linear models include like least mean square, perceptron SVM, logistic regression, naive Bayes. Non-linear models like kernel methods, neural networks, decision trees, data boost, random forest, etc. Right? So there is a natural extension from linear to non-linear models, that is kernel trick. Right? You should know that. And also we can categorize machine learning models from another perspective, namely whether it is based on probabilistic notion or non-probabilistic notion. Right? So probabilistic learning, we introduce logistic regression, naive Bayes, right? You should know what is philosophy of probabilistic learning, right? We're gonna assign probability on the probability distribution on the hypothesis space and research over the hypothesis who has the largest posterior probability. Right? This is the idea of probabilistic learning, right? This is different from the non-probabilistic learning. So also basic concepts and conclusions in computational learning theory. So what is PAC framework? What is PAC learnability, right? What is sample complexity bound? What is the generalization error bound, right? So you should understand it. Oh, sorry. You should definitely understand the concept, right? You're not required to memorize, recite those form of the bound. But if I ask you some understanding question, you need to hit the point, right? What is VC dimension and why should we introduce VC dimension? Very important concept. And how is the large margin principle derived by the generalization error bound, right? Again, this relates to how the idea of SVM is developed, right? We not only to know how, but also need to know why, right? Okay, and also principles to design machine learning model objective functions, right? Empirical risk minimization, including least mean square method, perception, artificial neural nets. Basically, we just create some loss, right? And loss function over the training data, so called empirical risk minimization, right? But we found that if you have like complex models, it often gives you overfitting results, right? So that's why we add some regularizer term in the objective function. So this idea is called regularized empirical risk minimization, right? A typical example is SVM. And also if you use map estimation for logistic regression, the prior of the weights actually forms another regularizer, right? And also from a probabilistic learning perspective, we have a maximum a posterior learning and maximum likelihood estimation. And learning algorithms, what is gradient descent, what is stochastic gradient descent, what are the pros and constraints for these two methods? You should be able to answer that, right? So basically, gradient descent gives you a very accurate estimation of gradient. If you can calculate the gradient, maybe you only use 20 steps, you can converge to the optimum, right? But if you use stochastic gradient, each stochastic gradient is very, very cheap, but it's wrong, right? So you might have like spend like hundreds or even thousands of updates until you arrive the optimal, right? But stochastic gradient descent is particularly useful for big data because for big data scenario, most cases you're even unable to compute one exact gradient. So, and we're gonna still we might also ask the practical question like how do you select hyperparameters, right? So why hyperparameters cannot be optimized? Like in SVM, what is the trade-off between the hinge loss and the large margin regularizer, right? We cannot optimize it. What's the consequence if you optimize it, right? How do you select it? So we have generally two strategies. You can hold our data set as a validation data set, or you can perform cross-validation. So again, if you want to conduct an effective review, I would like to suggest you to go through all the lecture slides because you haven't carefully gone through those lecture slides before to do the homework, right? It won't be very hard and very time consuming for you to review them again. I understand the details. And also go through all the homework problems. We release the homework problems answers. So you can access the answers and then look at what you have done wrong in your own homework submissions, right? But you do not need to go through the programming problems. That will be covered in the homework in the final exam. Okay, the last slide will be good luck. Any questions so far?
Excuse me, Professor. Should we keep the webcam on because my desktop system doesn't has webcam, but my laptop has webcam? So
You mean for the final exam?
yeah.
I don't see why you should keep the webcam.
Because in some universities, I think there is someone that staring at you that you don't cheat during the exam.
Let me think about it. Okay, I thought just it's just online. You can choose to open or not, but I'm not sure whether the online exam on cameras will have such kind of function, like require everybody to open the webcams. Let me dig it out, right? And then I will let you know, right, today. Okay.
Thank you.
And someone asked, how many questions will we have on exam? I cannot tell you the exact number of questions will be right now, but it won't be like it won't be more. The workload won't be more than a paper exam. Okay. So the paper for the paper problems, so okay, it's usually like 5 or 6 big problems and for everybody to solve. And of course, for online exam, you won't have big problems. You'll have more small problems. But I believe the workload should be almost the same or even smaller. Okay, another student asked, would it be possible to get some simple answer keys to the previous homeworks? Yeah, of course. We haven't released all the homework answers in Canvas. You can just look at the files in Canvas. You should be able to access that. Every time after we have graded the homework, we will release the homework's answers, not including the pseudocode not including the code for the practice problems. We cannot do that because I don't want those answers to be spread into the students who are going to register in next year, and that's not allowed. Okay. Yeah, I haven't mentioned that we're going to do an online exam on cameras, right? So basically, you're going to stay in front of your desktop or laptop, whatever. You just do everything online. Any other question? Okay, great. So anyway, I will investigate whether the webcam is recording conducting online exam on Canvas, because I've never used that before. I'm just trying to look at, and hopefully it will be a funny exam. Right? It's not be too boring, and it should be as fair as possible. Okay. Okay, great. So I'm gonna switch to can everybody see this slide? Practical advice for building machine learning applications.
Yeah, we can see it.
Okay, great. So the remaining like about 45 minutes to 50 minutes, we're gonna give some practical advice for building machine learning applications, and hopefully from this after this class, we're not only like understand those details and principles of this commonly used and very fundamental machine learning algorithm. We're also ready to deploy those algorithms or plugging those machine learning models algorithm into your real applications or research project, whatever. Okay, so that's why we would like to offer you some practical advice, right? So we're going to introduce talk about first, how can we diagnose the problem of a learning algorithm, right? So that includes error analysis, right? What kind of error dominates what kind of error dominates the machine learning system or the system which have your machine learning component embedded. You will see that in practice, machine learning is just one single component, one small component in your application. And then we'll talk about how to inject machine learning into your favorite task, right? So first, let us talk about how to diagnose your learning algorithm, right? So, but this diagnosis has nothing to do with checking a bug. We assume everybody is good at coding and debugging the code, right? So assume that, okay, your code is correctly coded, right? There's no bug on that, right? And suppose you train an SVM or logistic regression classifier for spam detection, right? You want to debug, you want to classify your emails received is a spam or not, right? So, and you obviously follow all the best practices for finding hyperparameters like cross-validation, like actual holdout data set. And it turns out your classifier is only 75% accuracy, right? And what can you do to improve it? So of course, everybody who, I mean, in your work, in your research, wants to apply machine learning techniques, you will face such kind of issues, right? Why my machine learning model works so badly, right? It's not good as my expected, right? And we assume that there is not bugs at all, right? We assume, okay, you're good. You haven't fixed all the possible bugs in your program. So very commonly, like people, 99% of people are just like, okay, I would like to add more features. Or I would like to clone a few features, or I would like to incorporate a few other features. This kind of feature engineering, right? Another comment, I just run for more iterations. Like previously, I tried to run for 100 iterations. Now let me increase it to 1,000 and see whether my performance increases. Right? Or I try a different algorithm. I might try stochastic training rather than LBFGS. I might use conjugated gradient descent, etc. Right? Or I might switch to another classifier. I do not use logistic regression. I try to use UVs, or even I try to use TensorFlow, PyTorch, right? Or I add some regularization term in my objective function. So there are many tricks, right? But the issue is that all those tricks, if you just blindly combine them together, you don't have you're much inefficient, right? And it's very tedious and prone to errors, right? Because you do not have any guidance, right? You do not know why. You do not know what is the problem, right? Like your car doesn't work. Your car stopped on the road, right? So you just step out and you just try to hit your car, use hammers and hit here, hit there, just blindly. Very unlikely. It's very unlikely that your car will get work again. So we need to make this diagnosis and fixing or improvement more systematically in practice. Otherwise, you'll see most of 99% of cases, those kind of work is meaningless. It doesn't work. So, but from what kind of direction should we diagnose? Should we test the problem of our machine learning model? Right? So we need to first identify what kind of problems our machine learning model has, right? If it doesn't work well. Right? So here are four common problems. First, your classifier, your predictor is overfitting the training data, right? For example, you train a neural network with 100 layers. Right? The second thing is that, okay, your model is not expressive enough to fit the training data. That means you underfit the data. So overfitting means that, okay, you have your predictor has high variance, but small bias, right? But underfitting, on the contrary, means that, okay, you have a high bias, although it is quite robust, right? And third thing means that, okay, your learning algorithm doesn't work properly, right? So your learning doesn't converge at all, then that's a big issue. And the fourth problem is, are you measuring the right thing? Maybe you have wrong measurement to indicate the performance of your work, right? And in that case, you need to redefine your measurement, okay? So what is the most obvious indicator of the overfitting. So we have discussed it in our class, right? So if you fit the training data so well, that might be a sign of overfitting, right? So if you observe that the training accuracy is much higher than the test accuracy, then this is a kind of evidence of overfitting. Means that your model explains the training data set very well, but poor in generalization, right? But what about underfitting? What about underfitting? Underfitting means that, okay, both your training accuracies and test accuracies are unacceptably low. So both are too low. That means, okay, you even cannot do well in predicting the training set. It means, okay, your model is incapable. That means your model cannot represent the concept well enough. So we can just look at how the training error and the test error vary along with the size of training data, right? And then we can view, okay, whether this problem is due to the model is too expressive or is too inexpressive, right? So if you just increase the size of the training data and then look at how your training error and the generalization error vary, you can draw some conclusions, right? So if you can observe some kind of large gap between the training and the test error, and it is more likely that your training model or your model you choose is a kind of overfitting, like you use very complicated neural nets, and turns out that the training error is very small, even with more and more training data, but the generalization error has a large gap with the training error. They won't meet, right? Just have a big gap. But how about the underfitting? I mean, too simple models. We can take a look, right? So if your model is too simple, that means that they underfit the training data. Well, your training error and generalization error seems to be very close, but you can see the error level increases a lot. Right? That means, okay, you cannot fit well the training data, so you cannot generalize well as well. So a common use trick, I mean, a diagnosis method is to just examine how your training errors curve and generation errors curve vary along with the size of training data. And then you can determine whether your model is overcomplicated or oversimplified, okay? Any questions so far? Okay, so I assume everybody is comfortable with this, and hope this can give you some kind of impression and guidance. Next time not next time, in the future, you apply your learning algorithm. You can use some kind of figures and graph to look into the behavior of your model, right? So generally, there are a variety of ways to improve your model, right? So if you incorporate more training data, obviously it will help with overfitting. Right? The more training data you have, the more difficult your machine learning model overfit to the training data. The training data is so large, right? At the same time, if your model are so flexible that it can fit a huge number of training examples, that means it will generalize very well as well, right? Because the more training data you have, the more representative your training data represents the input space, right? The instance space, right? And if you use more features, it can help with underfitting. Why? An idea? An idea? Why we should add more features to help with underfitting. Remember, because underfitting is caused by simplicity of your prediction of your model, right? So I now want to add some expressiveness of the model. One direct way is to add more features, right? If your feature is more can be expressive or can be discriminative to show some difference, right? Say to better help you to classify the two labels. Of course, if you add that feature, you increase the expressiveness of your model, right? So if you use fewer features, that means you throw out some features. It can help with overfitting, right? Because it might contain too many features. I just remove them. I simplify my model, right? And if you, in addition, add some other features, it can help with both overfitting and underfitting. Right? So how can we enhance better training? Right? How can we enhance training? You can run for more iterations to ensure, okay, your algorithm indeed converge to some optimal, right? Not in the middle. Or you can use a different algorithm, use different classifiers. And again, here, play with generalization is another common used way to preempt overfitting, right? So now I have to talk about some methods to diagnose the overfitting and underfitting behavior, right? And what is the commonly used strategies to deal with that? Adding features, adding more features, or removing a few features, or adding actual features, or adding regularizers, right? So let us talk about the third behavior. Right? Your learning does not converge. So how can you ensure your learning is converged? So if you use stochastic gradient descent, this is very common used for big data. This is really not straightforward. If you use LBFGS, if you can exactly compute the gradient, this is not a big issue. You can just look at the gradient and see whether their norm is 0 or close to 0. That's not right. But if you use the stochastic gradient, you cannot compute the full gradient. You cannot compute exactly. And so in such kind of cases, usually we need to look at another curve, right? That is how, along with more and more iterations or updates, your objective changes, right? So of course, if you stop your iteration at here, you haven't converged, right? You need to continue your iterations until you say, okay, your objective curve becomes flat. But sometimes it's still hard, even visually, because obviously from this point, from this number of iterations, your objective has not yet converged. But look at here, right? It seems converged, seems not. Right? So at this time, you need to reinvest. If you really want to, if your performance at here is enough good, you might stop here. I say, okay, although it is still slowly going down, but I think I won't need actual computational cost to even improve that because the gain is not that promising, right? But if you say, okay, this is not satisfactory, I would rather wait for more iterations. You can wait for more. Right? But if your learning curve looks like this is not correct behavior. Right? The objective won't fluctuate like this. Because usually your objective, your general trend is going down, right? But suppose we are minimizing objective, its general trend is going down, but if it perturbates very significantly, it won't. It shows that there must be a bug in your code. Okay. When someone asks, like, if I'm doing like stochastic gradient descent, your objective function, the curve won't be like so smooth, right? Because it's stochastic objective, then your curve will typically be have a little bit vibration. But you clearly see that this kind of vibration won't affect the general trend. The objective is going down. If the vibration is something like that, then you should stop and recheck the code. Okay. So now, what if you have problems in your algorithm convergence, right? So what kind of strategies should we choose, right? Here, we can track objective function for convergence, right? The typical way is to draw a curve, right? So now we have addressed the third problem, right? How do we discover that your learning does not converge, and what kind of strategies can we use, right? So any questions so far? So everybody is comfortable? Okay, great. So the last thing is also very important. Are you measuring the right thing? So so far in all of our homework assignments, we just use accuracy prediction, right? All the RMC, root mean square error of your regression problems. This is the most common measurement. But if your data set is unbalanced, accuracy might be misleading. So give you a particular example. Suppose we have 1,000 positive examples, only have one negative example. If I just give a very naive prediction, I always predict a positive. If you just use accuracy, okay, it is 99%, 99.9% accuracy. But does it really mean anything? The answer is no, right? Because in such kind of cases, this one negative example might be way more important than all those positive examples, right? So we might be more focus on the prediction of this negative example rather than some kind of overall accuracy, right? So, and you will see in practice, unbalanced training data are very unbalanced training tests are everywhere. Like for example, in medical diagnosis, most people won't have cancer, right? Just only a tiny portion of people have the possibility to have the cancer. That means, okay, all of like 1,000 examples, maybe 1 or 2 have cancers, right? You cannot predict everybody to have no cancers, although your overall accuracy might be 99%. This is a very important problem, right? So for unbalanced labels, we might have some more fine-grained criteria to measure the accuracy or the performance of the machine learning model. So commonly used a metric include like precision, recall, and F measure. Like precision is defined as like among examples that are predicted with label, what fraction are correct. Like you predict all of like 1,000 examples, you predict 99. You predict 500 examples to be positive, right? I want to say, okay, among your 500 positive prediction, how many are correct they predicted, how many are incorrect predicted, right? And recall is another metric, means that, okay, among all examples who are given a ground truth label, say out of like 1,000 examples, only and what are fractions are correct, right? Among your predictions, what fraction are correct? So it's kind of more like coverage. It's not and precision. It's more like accuracy. And F measure is kind of harmonic mean of precision recall. So you are not required to know the precise definition of precision and recall and also the F measure, but just give you a hint. Right? In unbalanced labels, we usually do not use overall accuracy because it's not meaningful at all. Okay. So any questions so far? Is everybody comfortable? Okay, great. So let's continue about the error analysis, right? So let's talk about like, if you plug in your machine learning component into some bigger application platform or system, how can we diagnose the problem of your machine learning component and also the system. Right? So in our class, in our whole class, machine learning code is everything. Right? It's the biggest component. This is a component you only need to care about, only need to focus on. But in practice, you will see where is machine learning. In practice, you're gonna always put machine learning in some bigger platform, bigger application, bigger system, whatever. So this system consists of a lot of other critical components as well, like a typical machine learning system or system that employs machine learning to do something, like Amazon's recommendation, like online advertisement or online trading, online bidding system, right? So we have some configuration system, like you have to set up the configurations from the domain experts, from users, or even from the companies, right? You have some data collection component, like in online advertising. You have to pass the database to record the interactions between user and the system, right? And you have to pre-process the data because there's a lot of noises. There are a lot of mistakes, and you have some format. You have some like wall format data, and you have some data verification procedure. You need to verify some kind of data are just noisy or harmful. Right? You need to get rid of them. And you have some feature extraction procedure, like some human coded feature or semi-automatic or fully automatic feature extraction procedure. And you have some process management tools, some analytical tools, and you have data fed into machine learning code. Machine learning code gives some results, and those results will be fed into analysis tools and process management tools. And those, after analysis and verification, the prediction might be used in some service, serving infrastructure, and interact with users. And also, there's also a monitoring monitoring module and see whether everything is working properly. This is a very complicated system. Machine learning is just one small component inside. And then if there's some kind of things happen in your output, in the running of your whole system, how can we detect which error is due to which component, right? And how much do each of these contribute to the error, right? So from the system perspective, error analysis is not that simple, right? It's not only looking into our machine learning component, because machine learning's input, machine learning's performance is also dependent on the output of other components, right? So we cannot separate them totally. So to illustrate this issue and also give you a hint how to conduct this error analysis, I would like to give you an example, a typical text processing pipeline, right? So this is a typical natural language processing application. So suppose you're given a piece of text. So first we're gonna separate them into words, perhaps do some stopping word remove, like remove those commonest words but meaningless words like a, the, and, she, or he, those kind of stuff, right? And then we do some parts of speech tagging task. This is a classical NLP task, and parts of speech tagging is not 100% accuracy for sure. And then after we have the past parts of speech tagging, we have words, and we feed them into tree parsing. Right? Tree parsing is to find some semantic structures inside the sentences, right? And after that, we extract features from parts of trees. We extract features from parts of speech tagging, features from words, and features even from original text into our machine learning-based application. This might be a classifier to predict whether this piece of text description is tend to criticize something, or tend to praise something, right? It might be some sentimental analysis. It might be some other analysis. A variety of models can be used, right? So, I'd like to mention that although we separate this whole system, this pipeline, into several steps, into several components, but each particular step might be machine learning driven as well. Part of speech tagging, parts of trees, all the state of the art methods are based on machine learning, right? That means all those components have their errors, right? And then a natural question will be like, how much do each of these components contribute to the error of the final application, right? So a commonly used strategy is to tracking error component by component. Right? How can we do that? We can plug in the ground truths for the intermediate components, right? And see how much the accuracy of the final system changes, right? Of course, you need to prepare a lot of the ground truths tests for each component, right? So first of all, we can run the whole application, that is end-to-end prediction. Okay, I say, okay, the accuracy is only 50%, 55% accuracy, right? And now I just preamp this component. Instead, I throw the output, I use some ground truth output from this component and feed them into the remaining components, parts of speech, parts of trees, and then ML applications. Okay, I say, okay, I increase 5% accuracy. My final accuracy gives 60% accuracy, gives 60%, right? And then to see what is the error for the remaining components, I can preempt parts of speech tagging, right? And I remove this component. Instead, I feed the downstream components with some ground truths. I say, okay, the accuracy dramatically increases to 84 accuracy, right? And similarly, I can preempt the parse tree component. I further increase 89% accuracy. And finally, I give all the ground truths I have 100% accuracy. So from this, what can we observe? If you want to improve the whole system, which component should we first look at? Any idea? Yes, right? Someone said, okay, look, if we use ground truth parts of speech, my accuracy increases from 60% to 84%, right? This is a dramatic improvement. That implies that, okay, this component has a big problem, right? We definitely need to improve this component. Of course, we need to improve the remaining components as well, but the gain is not that much as the improvement over this parts of speech tag. Right? So errors in the part of speech component hurts the most, so we should fix that issue as well, right? So this is called ablative study, right? And we can use that for feature engineering as well, right? So usually seeing with features, suppose we have a collection of features and our system does well, but we don't know which features are giving us the performance. Right? So in this kind of case, we can evaluate a simpler system that progressively use fewer and fewer features to see which features give the highest boost. This is important because we need to know which feature are most discriminative or most informative, and we need to know, okay, why it's so informative. And if we say, okay, if we get to know why, then we're enlightened to create new features which can further help with us. Right? It also helps interpret predictions, diagnosis errors, and provide an audit trail. Right? So don't view machine learning components as black box. This is a very bad trend recently in machine learning research. People just throw everything into a black box neural networks and just wait for the results, better results. This is more like alchemy. It's not scientific study. We need to know why. Okay. Those are mainly some commonly used strategies and also very useful suggestion for you guys if you in the future want to apply your machine learning in any tasks you want, right? So now let us talk about how do you inject machine learning in your favorite task, right? So suppose you are trying to classify fish, right? So you want to build a classifier that identifies whether a real physical fish a Solomon tooling, right? How do you go about this? So from like academia point of view, right, we're gonna first carefully identify features, get the best data, and then we need to design a software architecture, maybe design a new learning algorithm. Then we're gonna implement it and hope it works. Right? So it's kind of doing everything fundamentally well, and we ensure every step is perfect and slowly until we see the outcome. Right? So there obviously is some advantage. Maybe even a new learning algorithm will be provided as a common use way in research, right? So, but in practice, I mean, especially in industry, your boss won't give you like 3 months to help to know the results. So then, what is the most common approach in practice and in industry? We're going to use hackers approach. So we first implement something. We use very stupid, naive classifier and say what is performance. Say I can just find some linear regression or linear classifier and pick up and random pick up, not randomly. I just give a rough look and I feel okay. These 10 features might be good, and then just feed those features into my classifier and see what is going on. And then we're gonna iteratively improve our classifier, either from adding more features, and engineering more features, or switch to more complicated models from SVM to kernel SVM, from kernel SVM to artificial intelligence, to artificial neural nets, etc. Right? So the benefit of this hackers approach is that it's faster. You can release your new version very, very fast. You can give quick feedback, and even you haven't perfectly solved the problem, you might have like usable one. Right? So in many cases, you'll see that actually, I mean, in practice, we're not seeking for perfect solution. We're seeking for usable solution. Right? We're seeking for something, okay, it's not too bad, it's fine. Okay? And another common used, another benefit of this hackers approach is that through iterating, right, I actually have generated a bunch of baselines. And finally, if I arrive at some very good solution, those baselines are the best demonstration of the evidence to allocate my solution. Okay, so in practice, never choose this one. Right? Choose this one. Choose this kind of strategy. Any question? Okay. Okay. So, and also, when you design your machine learning model algorithms, you also need to look at whether you have doing the right evaluation metric, as we mentioned before, right? So if you have very unbalanced examples, if you're just doing, if your objective function only evaluates the overall accuracy, that might not be beneficial. You have 1,000 examples, only one negative examples. Okay, your objective aims to minimize the whole, maximize the whole accuracy. That won't be effective. Right? You need to weigh the negative examples prediction much more important. Right? Another important and very critical, actually it's very critical suggestion is that beware of contamination. So what does it mean by contamination? Contamination means that don't overlap your training with the test. So remember, learning is always a generalization to new examples. That means, okay, during training procedure, you never allow your machine learning model to see the test examples. Otherwise, all the results, all your testing performance is meaningless at all. Okay, and this is commonly made mistakes by machine learning practitioners, even for very senior and very experienced people. So in any cases, like when you first try your new models and say, okay, your accuracy is incredible incredibly good, don't celebrate. Be careful and check whether you happen to mix your training and test dataset. Okay, so always be suspicious for perfect predictors. Right, there's no free lunch. And also be aware of bias versus bias trade-off, right? Usually, if you choose very complicated models, you have overfitting issue. You might overfit the trained data so good, but then you have a large variance, right? Overall, your generalization error is large. But if you choose too simple models, you might underfit the trained data, although you have a small variance, right? And also, in practice, we're always dealing with high-dimensional input features. It's not as intuitive, as natural as you can imagine in the two-dimensional space or even three-dimensional space, because we do not have proof by picture. You can only imagine the high-dimensional issue. There's a so-called curse of dimensionality. And also, in practice, a theoretical guarantee may only be theoretical, right? You might happen to say some theoretically very good machine learning models and algorithm gives you very bad performance. So don't be disappointed on that, or don't feel weird, because many theoretical conclusions are drawn based upon strong assumptions, and very probably your own applications won't satisfy the strong assumptions on that. So that's why you see the performance of your theoretically perfect classifier is not as good as you expect. Okay, and experiments on real data are equally important. That's why in machine learning research, like if you only say something theoretical, that's not enough. We'll always need you to test your models and algorithms in real world data. Even like if you just do experiments on simulation data, that's far from enough as well. And in practice, although big data can provide you much more information and can help you improve performance, but big data is really not enough. You need more smart way to conduct the training. You need more smart way to design model and algorithms. But usually more data is always better, and cleaner data is even better. In practice, you spend a lot of time in dealing with noisy data, dealing with incorrect data, dealing with data have missing entries. Right? So you have to spend a lot of time to pre-process the data to make it clean and informative enough and for machine learning algorithms. So if machine learning model doesn't work as you expect, don't believe the algorithm itself, don't believe the model itself. First look at whether the data pre-processing pipeline is effective or not. Right? So learning requires knowledge to guide learner. So machine learning is not a magic wand. Okay. So what kind of knowledge can be useful to design the machine learning models or algorithms? Right? So which model is the right one for this task? Right? So this is kind of need some experience. Right? We know some kind of applications, linear models should be more than sufficient. Like on click-through prediction, people find, okay, logistic regression works really well, although there's kind of a tendency to add some deep neural nets, but those deep neural nets are really not deep, just 3 levels, right? And also combine a bunch of linear models. It's called a wide deep model. If you're interested in, this is a state of art on an advertising system, right? And what kind of problems are more appropriate for decision trees? Like if you want to do something which requires your model to be enough transparent and interpretable, decision trees is wonderful choice. Like in many expert systems, people not only need to know whether this performance is good or not, they also need to know why, right? And it works in other kinds of applications, like deep neural nets perform very well, like image classification, like voice detection, those kind of things. But deep neural networks obviously cannot be used for disease diagnosis, although there's kind of hype saying that, okay, deep neural nets can be used to diagnose disease, but can you, I really feel safe to use that, right? Who can take use, who can be in charge of the error prediction, right? Obviously, we need some transparent model, right? But those are totally like domain dependent, right? You have to gain some experience on this, on your own areas. You will get a sense in general in this area which type of models, algorithms are more favored to the other models and algorithms. Right? Also, which learning algorithms. So does the data violate any crucial assumptions that were used to define the learning algorithm or model? Does that matter, right? And like in naive, we know that it has some strong independent assumption, condition independent, right? But you will find out, okay, in many applications like text-dependent applications, such kind of conditional independence is okay. Even the data breaks this conditional independent assumption, right? And also, feature engineering is crucial. You see that, okay, in most cases, smart model is not that important. Feature engineering matters really much, right? So that implicitly, these are all claims about nature of the problem. You should have a very deep understanding of the problem for you to develop really working machine learning algorithms. So here are some miscellaneous advice, right? So we can always start from simple models, right? We'll not try to build up very complicated models from scratch. That will hinder you from understanding the nature of the problem, right? So it's always good to start from simple models, from a few features, and trying to increase the models to more complicated feature engineering. And from this iteration procedure, you will better and better see the nature of the problem, and you will better improve the performance, okay? And also, a common rule of thumb is that ensembles seem to work better. And think about whether a problem is learnable at all. Some kind of problems might not be fit for machine learning. Right? It's not a learning problem. In that case, if you're trying to use machine learning, you're trying to step back and think about whether this is a real learning problem. Okay. Yeah. So now we have finished everything in this semester, and I'm glad to stay together with you guys for this whole semester. This is a good journey to look at machine learning. And also, I'm pretty much sure you guys have spent a lot of time and efforts in doing this homework. And hopefully, you get something you feel good and you want from this course. And from my personnel, I'm happy to work with you guys and happy to discuss with you guys, and I sincerely wish all of you good success in the future. Okay. And on Thursday, there won't be any class, but I'll still hold the 1 hour office hour. If you're interested to ask any questions, feel free to join into the Zoom office hour. Okay.
Thank you very much.
Yeah, thanks. And again, if you have any question, I still have the office hour at 2. So if you have any problem, just feel free to connect in. Okay, thanks. Thanks, guys. Yeah. Yeah.
Thank you.
Thank you. Yeah.
Thank you.
Thanks. Bye-bye, guys. Yeah. I'm waiting for you guys to quit. Yeah. I'm enjoying seeing so much messages. Thank you. Okay, thanks. Thanks. Yeah.